The universe is censoring you, and here's why. He lowers the last shutter and kills the lights. On the screen, two bright bands blaze to life, then, as if embarrassed, dissolve into a thin spray of dots. He flips a switch, the dots sharpen into razor stripes. Another switch, the stripes vanish again. He laughs once, quiet and uneasy. The machine isn't broken. The universe is refusing to commit. This lab trick will haunt everything that follows, because what looks like a party trick is actually a code, an access policy on reality. To see how the universe hides its tracks, we have to go back to the first glitch, the vanishing path. The first glitch, double-slit and the vanishing path. They thought they were just firing bullets of light. Two slits, a screen and a beam. Open both slits and you expect two bright patches. Instead, the screen blooms with alternating bright and dark fringes interference, as if each photon were a wave interfering with itself. Fine, call it a wave. But then turn the beam down until photons arrive one at a time. The fringes still build up over hours. A single event spread across possibilities somehow knows both paths. Get this, if you ask which slit it went through, the pattern changes. Put detectors at the slits to track the path and the stripes vanish. You recover two fat blobs. Particles march through one slit or the other. The moment the path is recorded, the interference dies. Take the detectors away and the interference reappears. It's the first time physics whispers. It's not just what happens, it's what can be known. Here's the thing that gnaws at people. It isn't the act of seeing with your eyes that matters, it's the information being available in principle. A faint scatter off a dust mote, a whisper of a field, anything that leaves a recoverable trail counts as which path information. The universe seems to run an audit. If path information exists, the interference is off limits. If no such record can exist, interference is allowed. It reads like a permission system. Now remember, this isn't metaphysical hand-waving. It's been pushed hard. Physicists built delayed choice experiments, where the decision to preserve or erase which path information is made after the photon has already hit the slits. The results hold. When the setup would allow the path to be known, interference doesn't appear. When the setup ensures the path can't be known, even if that lock is applied later in the apparatus, interference emerges in the tallied coincidences. They didn't find time travel. They found that what counts is the logical availability of information in the total arrangement. But here's where it gets crazy. You can tag the photon with a subtle marker, say, a polarization twist tied to each slit, so that in principle the path is encoded. Interference disappears. Then you route the photon through a device that erases the correlation, scrambling the tag so the path becomes unrecoverable. Suddenly, in the right subset of detections, the interference returns. You didn't undo the past, you removed the record. The universe acted like a strict librarian. If a path record exists, no interference. If the record can't exist, you get the fringes. Pause on the human moment. A young grad student stares at a black screen waiting for dots to accumulate. The lab smells like warm electronics and old coffee. Her advisor told her this would feel wrong. She watches 1,000 tiny pinpricks bloom into a ghostly zebra. It feels like the machine is choosing when to tell the truth. Meanwhile, something else is happening in her head. If information is the gatekeeper, then the limit isn't just energy or distance. It's access. The universe might not be hiding things behind brute force walls. It might be hiding them behind conditions. You can't see the wave and the path at the same time because those are different questions. Ask one, and you lock the other behind a door you just closed. This was the moment everything changed for how some physicists talk about reality. The double-slit becomes a parable about limits. Not you don't have the technology, but you aren't allowed that combination of facts. It's a censorship code that doesn't need an enforcer. The rules live in the math. Complementary observables, uncertainty relations, the no cloning of unknown quantum states. They all rhyme with the same idea. Information can't be copied freely, tracked everywhere, and still behave like a wave. Unknown to most viewers, there's another twist. It isn't measurement in the Hollywood sense that collapses anything. It's decoherence, uncontrolled entanglement with an environment. A photon brushes past a stray molecule and leaves a whisper of which path. That whisper propagates into a room full of air, then a building, then the world. The path becomes, in practice, knowable. Interference vanishes. Remove the environment, shield, cool, isolate, and the interference returns. It's not magic, it's bookkeeping. 3 days earlier, the same grad student had tried to peek, gently turning the detectors down to barely register. The fringes blurred but didn't disappear entirely. That's the other rule: partial knowledge, partial interference. The contrast of the stripes maps to how much path information leaks. The less you could, even in principle, recover, the sharper the wave-like pattern. It's as if the universe charges an interest rate on certainty. What nobody knew at the time, standing by that screen, was how far this logic would travel. To black holes, where information seems to fall and vanish, only to whisper back in radiation years later. To gravitational wave observatories pushing against quantum noise, forced to reshape the vacuum to listen harder. To pulsars across the galaxy, whose ticks carry spacetime's murmurs only when correlated just right. The same question keeps surfacing: what can be known, by whom, and when? But hold that thought. For now, keep your eyes on those vanishing stripes. This is the first glitch in our story. A tiny, stubborn experiment that teaches a harsh lesson. Reality isn't a menu you can order from freely. Every question you ask locks another door. And once a record exists, even a fragile one, the universe treats the answer as final. The speed limit and the toll. Light, causality, and channel capacity. The grad student walks home under streetlights that hum like old radios. She keeps replaying the vanishing stripes, but another constraint presses in. Nothing outruns light. Not a rumor, not a push, not a clever hack. That speed limit isn't a traffic rule. It's the scaffolding that keeps cause before effect. Try to send a signal faster and you scramble the order of events for someone else's clock. Causality tears. The universe says no. Get this, if information has to live inside light cones, then every message you send is fenced by geometry. The future you can influence is a cone widening at light speed. Everything outside stays mute until time brings it inside. It's a map of who can know what and when. That map is the first half of the censorship code. You can't reach beyond the cone without rewriting time. But there's a second half, and it hits when you try to talk through the cone. Even if light speed is generous, the channel itself takes a toll. Noise lives everywhere, in the thermal wiggle of electrons and the quantum jitter of fields. Claude Shannon, working in a wartime lab, framed it like a wager. You can send symbols down a noisy wire, but the wire will flip some. The question isn't, can I send forever? It's, at what rate can I send reliably? He gave the answer a name: capacity. Here's the thing. The microscope in her lab and the fiber in your phone are both channels. Each has a maximum rate measured against its noise. Pile on more power and you don't get infinite clarity. You get smearing, heating, crosstalk. There's an optimal code, a sweet spot, but there's always a ceiling. That ceiling is brutal because it isn't taste or budget. It's mathematics. Past capacity, errors drown meaning, and no decoder can resurrect what never made it through. She hears this again in a different key the first time she tour a radio observatory. The guide points at a dish listening for whispers from a pulsar 10,000 light-years away. We integrate for hours, he says, because noise doesn't stop. You have to average it down. The universe isn't quiet. To know more, you wait longer or bring more area. Either way, you pay. Meanwhile, something else is happening a continent away. In shafts of vacuum, LIGO's lasers bounce between mirrors, straining to hear spacetime stretch by a fraction of a proton's width. They hit another toll booth: quantum noise. Shot noise from the grain of light. Radiation pressure noise from the light punching the mirrors. Squeeze the light, reshape the vacuum's fluctuations, and you can trade one noise for another, move the wall a little. But there's a wall. They didn't hit shoddy engineering. They hit the standard quantum limit, born from the same bookkeeping that killed those stripes. Now remember, capacity isn't just about the watts you pour in. It's about bandwidth, the range of frequencies you can occupy, and about the temperature of your environment. Landor's principle sneaks in here. Every bit you erase dumps heat somewhere, at least kT-ln2 of it. That heat becomes noise. The effort to make a clean record dirties the room. Try to build a daemon that separates fast molecules from slow, and you discover the cost hiding in its memory. The toll is universal. Moving, storing, erasing information leaves a thermal wake. She pulls at that thread and finds a limit on speed that isn't about rockets. The Margulis, Levitin bound, the quantum side of the ledger, says there's a minimum time to evolve from one distinguishable state to an orthogonal one, set by your average energy. There's a fastest clock hidden in physics, and even a perfect processor ticks no faster than that. Computation is a kind of motion through configuration space, and it has a speed limit too. While all this plays out, astrophysicists stitch together a different kind of detector, a pulsar timing array using millisecond pulsars as clocks scattered across the sky. Each tick travels at light speed, soaked in noise from interstellar plasma and clock drift, but correlate many pulsars over years, and a pattern leaks out. A quadrupolar correlation, the Helling's, Down's curve, a fingerprint of a gravitational wave background. The trick isn't brute force hearing, it's coding the galaxy as a receiver and paying with time. Capacity again. Widen your effective bandwidth by adding sources, lower your noise by averaging. The toll is patience and calibration. This was the moment everything changed for her sense of hidden. It wasn't that secrets were tucked behind walls you could blow open with more energy. They were throttled by the joint laws of causality and capacity. You can't shout past a light cone, and you can't whisper below the noise floor faster than Shannon allows. And when you try to clean the message, you heat the room. Here's where it gets personal. She tries to build a better measurement in the lab, cooler detectors, darker rooms, smarter codes. Each success feels like prying open a shutter, but every 30 seconds a new constraint shows up. The power supply hum sneaks into the data. The refrigerator dumps heat that ripples into the optics. The squeezed light lowers one hiss but raises another. Progress is real. The toll booths are too. So the code sharpens. Spacetime sets where information can go. Noise and thermodynamics set how much of it survives. Quantum rules set how cleanly you can extract it. The universe doesn't just hide by distance. It hides by rationing your access, charging you in time, energy, and entropy for every extra bit you demand. Planck units, pixels, frames, or just convenient. She keeps a sticky note over her bench. 1035 meters, 1043 seconds. Planck length, Planck time. They read like the fine print at the bottom of the universe. People talk about them like pixels and frames, as if space were a screen and time a refresh rate. It's tempting. You want the world to snap to a grid so you can count it. But here's the thing. Those numbers aren't carved into bedrock as a hard lattice. They're built by mixing three constants: the speed of light, Planck's constant, and Newton's G. Put them together, and you get the scales where quantum and gravity stop ignoring each other. That's why those units haunt theorists. Not because we've seen the pixels, but because this is where two different rulebooks both insist on being heard. Meanwhile, something else is happening in the literature. People argue about whether the Planck length is a real cutoff, a smallest possible tick of space, or just a convenient yardstick we made from our favorite constants. The lab isn't going to settle that this week. LIGO doesn't see a grid. Pulsar timing arrays don't either. Instead, she hears the question reframed. Even if the world isn't literally pixelated, could there be a limit to how finely information can be packed into a region? Now remember the Blackboard lessons about entropy. John Bekenstein took gravity seriously and found a bound. The maximum information inside a sphere doesn't scale with volume. It tracks the area of its boundary. That sounds like her sticky note, but sideways. Less space has pixels, more. The bookkeeper only lets you write so many bits on the surface before anything inside collapses under its own accounting. The holographic hint lands. If there's a censorship code, maybe it's a boundary rule, not a grid rule. Get this? If you try to cram more detail into a region than the bound allows, you don't get sharper pictures. You get a black hole. The universe enforces the limit by making your hard drive gravitationally self-destruct. It's a nasty kind of compression. Exceed capacity and your data becomes an event horizon. Whatever Planck really is, she can feel the teeth of a deeper principle. The fine print shows up as area. She tries to translate this into lab instincts. If there's no direct microscope for 1035 meters, what would a Planck scale limit look like downstream? Maybe as a floor-to-measurement noise you can't squeeze past. Maybe as a ceiling on how fast a system can compute reliably without turning into heat. Margins where attempts to sharpen reality bounce off thermodynamics and gravity together. Planck doesn't need to be a pixel. It can be a toll booth where two departments, quantum and geometry, share one cashier. Here, S where she hears from older colleagues who chased quantum foam, those old pictures of spacetime bubbling at tiny scales. Cute metaphor, shaky prediction. No resonant hum of foam in interferometers, no easy signatures in cosmic light. But the absence of a pixel click isn't silence. It's the same pattern as before. The universe hides by redirecting the question. You don't get to zoom in. You get to count how many distinct messages can live in a patch before gravity edits them. 3 days earlier, she'd been reading a paper tying computation to energy and time. Minimum steps per joule, minimum time per step. It rhymed with the sticky note. Combine those with the Bekenstein bound and you get something like a cosmic budget sheet. A maximum number of operations a region can perform before its own heat and gravity push back. Planck lurks in the constants, but the visible rule is about how many clean distinctions, bits, you can make before the ledger flips red. Meanwhile, out on the horizon of theory, black hole physics hits the same chord. The entropy of a black hole scales with area in Planck units. Hawking radiation leaks information in a slow, coded drizzle. The page curve says the ledger balances in the long run. Whether or not space is pixelated, the accounting is, and the unit on the invoice is built from those same constants. Planck shows up as the size of a bit written on the boundary. She thinks back to the double-slit. There the code said, you can't have full wave and full which path at once. Here, the code says, you can't store unlimited distinctions inside a region without paying in curvature. Both are access rules. Both are about which questions the universe lets you ask together. Planck, then, isn't a brick. It's a watermark that appears when you try to combine questions from both rulebooks. Now remember the human moment. She peels the sticky note off and writes in smaller letters. Not pixels, policy. It keeps her honest. Because if you chase Planck like a grid, you start seeing ghosts in your instruments. If you treat it like a policy, you design better questions. You ask about capacities. How many qubits survive decoherence in this volume, at this temperature, with this gravity? You ask what must happen when your code exceeds the boundary's allowance. This is the moment everything shifts. Planck units move from myth to mechanism. They don't tell her that space is chunky. They tell her where the universe's two auditors meet to reconcile the books and what currency they use to do it. She doesn't need to see the pixels to feel the limit. It shows up as the rate you can compute, the bits you can store, the heat you must dump, and the area that quietly tallies it all. Landor's bill, the heat of erasing and the cost of knowing. She thought the hard part was getting the data. Turns out the receipt comes later. In the quiet after an experiment, when the files are saved and the sensors spin down, something subtle but absolute kicks in. Landor's rule. Erase a single bit, truly erase it, and you owe the universe at least kT ln2 of heat. Not a suggestion, a floor. The cost of clearing a memory cell, of resetting a register, of saying start fresh without ambiguity. Every act of forgetting leaves warmth somewhere. Here's the thing, this isn't about clunky hardware. It's about logic. You can compute reversibly and dodge the toll for a while, but the moment you compress outcomes, discard branches, or overwrite a register without keeping a perfect history, you've paid. The demon in Maxwell's thought experiment learned this the hard way. It could sort fast molecules from slow and lower the gas's entropy, but to keep working, it had to clean its notebook. The heat that spilled in that cleanup repaid the debt. Entropy never lost. The bookkeeping just moved columns. Meanwhile, in the lab, she feels the bill arriving in mundane ways. A firmware update that writes logs to the same disk again and again. The data pipeline that prunes raw streams into tidy summaries. Each reset warms a component, nudges a bath temperature, adds a flicker to the noise the next run must average down. The act of knowing, of making a record that favors one set of bits and discards the rest, creates heat. The act of preparing to know again by erasing creates more. Now remember the earlier rules. A measurement is a controlled entanglement with a pointer that you can read. That pointer needs a standard state before the next shot. Reset it and Landor taps you on the shoulder. You wanted clean, fresh, ready states, pay in heat. Try to hide the heat in a refrigerator and the fridge dumps it to the room. The room breathes it into the building. Follow it far enough and your measurement spills entropy into the world. The cost of certainty ripples outward. Get this, there's a strategy to dodge the worst of it. Bennett showed you can compute in a way that's logically reversible, uncomputing ancillas and carrying your garbage bits forward like a tidy traveler. But the universe is merciless about one detail. To deliver an answer to someone else, to compress your past into a small payload, you must eventually throw away branches. If you never erase, you're just moving the mess. To communicate a conclusion, to turn sprawling microstates into a crisp yes or no, you erase. The eraser's warmth is the price of clarity. She hears this toll in the analytics of her own microscope. The detector's firmware takes a continuous stream and bins it into counts. Binning is erasure. The compression algorithm that saves space on the server is erasure. The thresholding that decides event or no event is erasure. Each is a little furnace that must be paid for in cooling power and noise budgets. Every choice to know more cleanly here means knowing a bit less cleanly there because the heat goes somewhere. Meanwhile, information theorists phrase it in the cleanest way possible. Entropy is missing information. When you erase, you increase missing information about the erased degrees of freedom. That missing information doesn't vanish. It shows up as heat in the environment's microstates. It's the same ledger from the double-slit, but now the column headings are bits kept, bits tossed, and heat emitted. The code is consistent. Trackable distinctions demand energy. Discarded distinctions demand entropy. 3 days earlier, she tried a trick she'd read about. Use reversible logic to post-select on rare events without erasing intermediate junk. It worked, until she had to report the outcome. The moment she shared a 2-bit answer from a 1,000,000-bit scaffolding, the scaffolding had to be cleaned or forever maintained. Cleaning cost heat. Maintaining cost memory and energy. Either way, the bill arrived. Here is where the cosmic angle snaps into focus. Black holes hoard entropy on their horizons. Hawking radiation carries it away late, like a slow, careful uncompression. If the universe preserves information overall, then anything that looks like deleting must export its cost. Landor's principle is the local face of that global honesty. You don't get to wipe without warming. You don't get a free lunch. You get a lunch tab stapled to your detector. She sits with a simple, brutal corollary. Knowing is thermodynamic, not just philosophically, literally. Each bit you lock down has a life cycle. Prepare the pointer, entangle, read, reset. The only step that can't be made arbitrarily gentle is the reset that discards alternatives. That's the heat. That's the toll. Push your experiment to higher rates and your erasures pile up, heating the very environment you're trying to quiet. The code protects itself. Try to pry open more certainty, and the room hisses back. Now remember the human moment. She stands by the cryostat, hand on the gleaming steel, feeling the faint warmth of 1,000,000 erased bits. Data isn't free. It leaves a temperature signature on the world. Landor didn't invent the bill. He found where the universe had hidden it, in the act of forgetting. Black holes as firewalls or vaults, the Bekenstein Hawking ledger. She first met a black hole not as a monster but as a number. S equals A4 in Planck units. Entropy equals area, not volume. It felt like a clerical error until the implications hit. If entropy measures how many microstates could hide behind a macrostate, then a black hole's how many ways scales with its surface. The ledger of possibilities is written on the horizon. Try to stuff more states inside than that boundary allows, and gravity answers with a horizon that grows to keep the books balanced. Here's the thing, Hawking's calculation added a second entry line, radiation. Quantum fields near the horizon were predicted to make the whole glow slowly evaporating. Put those together and the story turns tense. As the area shrinks, the entropy must fall, meaning information should spill out. But Hawking's original derivation said the radiation looked thermal, featureless. If it's featureless, the ledger doesn't balance. You'd lose distinctions forever. That's the information paradox. Now remember the page curve, a thought experiment that refused to let the books go red. Don Page argued that if the universe is unitary, the entropy of radiation rises early, because you're dumping random-looking pieces into the environment, then peaks at the page time and falls, as correlations reveal the interior's degrees of freedom in the outgoing quanta. The curve sketched a vault, not a shredder. The information is locked in early and only released when the lock cycles to the right point. Meanwhile, something else was happening in theory that made the sketch look like a mechanism. In toy universes with good bookkeeping, at spacetimes paired with boundary theories, the island story arrived. The entanglement wedge that tells you which bulk regions are encoded in a given boundary system can jump. Past the page time, parts of the black hole interior belong by encoding to the radiation's description. The ledger updates. The radiation holds the key, and the vault door has moved. Get this, if that's the rule, the horizon is neither a brick wall nor a liar. It's a boundary that changes who's allowed to reconstruct what. Early on, the outside doesn't have the code. Late, it does. No firewalls required to burn infalling observers. No shredding required either. The universe isn't cheating, it's rotating access permissions over time as entanglement patterns shift. She hears the Hayden, Preskill twist like a rumor from a future experiment. Once a black hole is past the page time, it behaves like a mirror for new messages. Toss in a diary, wait for a scrambling time, a short logarithmic delay, and the next trickle of Hawking radiation, combined with what you already collected, contains enough to reconstruct the diary. Not because radiation suddenly carries explicit bits with labels attached, but because the code that encodes the interior and the exterior is now on your side. Capacity and delay, again. But there's a catch that sounds like policy. Reconstruction depends on what you know and how cleanly you can process it. It's not a button you push. It's a decoding problem at the edge of thermodynamic budgets. Even if the information is there, pulling it out demands correlation across vast datasets and erasure of staggering amounts of junk. Landor waits on the other side of the vault. The ledger balances in principle. In practice, you pay heat to learn. She looks at the Bekenstein bound with fresh eyes. It never said, no secrets inside. It said, no more bits than area allows. A black hole at that bound is a maximally packed drive. The vault metaphor becomes literal. The surface is the index, the place where the count is kept. The interior's detailed microstates are scrambled beyond recognition to any local probe. Ask for too specific a combination of facts about those states, and you find you don't have the access rights until late-time correlations roll in. Meanwhile, the firewall debate plays like a family argument at the dinner table. One side says you can't have smooth horizons, unitary evaporation, and local effective field theory all at once. Another side points to how codes work. The same logical qubit can be redundantly stored so that no single local view sees a violation, yet the global description stays consistent. It's not that the infaller is incinerated. It's that the outside observer's reconstruction privileges don't include what the infaller feels until the ledger flips. Two perspectives, two access policies, one global book. Here's the human moment. She stands by a whiteboard covered in areas and logs, tracing a curve that rises, peaks, then falls. A colleague asks if the world is kinder or crueler for it. She shrugs. It's honest. The black hole isn't a bonfire that destroys meaning. It's a vault that withholds it until the world is ready to decode. And the price of the key is time, patience, and the heat of erasing everything you didn't need. The holographic constraint, when surfaces dictate reality. She hears the rumor before she sees the math. Reality might be written on its edges, not poetry, accounting. The Bekenstein hint becomes a doctrine called holography. The claim is blunt. The maximum information in a region scales with its boundary area, and in certain universes we can control on paper. Everything inside is exactly encoded on a surface far away. Volume becomes a story the boundary tells, with limited ink. Here's the thing. This isn't a metaphor in those toy worlds. In AD-SCFT, gravity in a bulk space is dual to a quantum theory living on its boundary. The grad student reads the papers at midnight and feels the switch flip. Fields, particles, even black holes in the interior correspond to operators and states on the edge. Bulk geometry becomes a map of entanglement patterns in the boundary. If you know how the boundary is entangled, you can literally draw the interior. Meanwhile, something else is happening in the language of error correction. The best way to understand the duality is to think like a coder. Logical information, the interior, is redundantly encoded across many boundary degrees of freedom. Lose a patch and you can still reconstruct the message. That's why different boundary regions can recover the same bulk bit. No contradiction, just a code with overlap. Access depends on how much boundary you control and how it's stitched. Now remember her sticky note about policy, not pixels. Holography sharpens the policy. The surface doesn't just throttle how many bits exist, it decides who can read which interior bits. Choose a boundary region large enough and your entanglement wedge, the part of the interior you're entitled to reconstruct, grows to include more bulk. Shrink your region and the wedge retreats. The interior isn't an absolute place. It's a privilege that shifts with the reader. Get this, the Ryu-Takayanagi formula ties it all together with a piece of geometry. The entropy of a boundary region equals the area of a minimal surface in the bulk, plus quantum corrections. Draw that surface, and you've drawn the leading term in how many interior states are hidden from that boundary. When the minimal surface jumps, access jumps. That's how the islands in black hole evaporation emerge. The minimal surface changes, and suddenly the radiation's wedge reaches behind the horizon. She tries to translate this to lab instincts and ends up staring at tensor network diagrams that look like spider webs. Each node is a little unitary, each leg a bond. Contract enough of them and you build a geometry from entanglement. Cut the network to isolate a region, and the number of legs you sever. The cut tracks the entanglement entropy, just like the area in Ryu-Takayanagi. Change the pattern of bonds and the curvature of the emergent space bends. It's not stone, it's structure in the correlations. Meanwhile, she can't ignore the human angle. If interior reality is a code word spread across an edge, then asking what's really inside, without specifying for whom, is sloppy. Access becomes the operative word again. A small boundary lab sees one wedge. A bigger collaboration, pooling data and control, sees deeper. Reality grows with coalition. That's not solipsism. It's the architecture of a code that resists local tampering and tolerates noise. Here, S where the censorship code feels explicit. Surfaces dictate. No boundary region below a certain size can jointly know a certain bulk fact. Try to combine incompatible reconstructions from disjoint regions, and the code won't let you. Like the double-slit's complementarity but organized across space. Different cuts of the boundary support different, non-simultaneous bulk descriptions. You can't have all of them at once without owning the whole edge. Permission by partition. 3 days earlier, she'd walked a colleague through a paradox. Two observers, each holding a boundary patch, both claimed to reconstruct the same interior qubit. "Isn't that cloning?" he asked. She pointed to the overlap of their wedges and the code's redundancy. Neither has the qubit alone in a way that violates no cloning. Each has a different recovery map. Neither can hand you a literal copy without reference to the full code. The qubit isn't duplicated, it's protected. Now remember the toll booths. Reconstruction isn't free. To pull a bulk bit from boundary noise, you need control, time, and erasure. The code resists small errors, which is exactly what you want in a universe with decoherence and heat. But that resilience also means you can't surgically extract interior facts with a tweezer. You must marshal large, correlated actions on the boundary. Capacity and cost show up even when the math says in principle. She finishes the paper stack and looks back at the lab. A cryostat, a laser, a server room, all surfaces, all boundaries with budgets. Holography isn't telling her that our universe is definitively at S, it's teaching a style. When the books are honest, surfaces rule. Entanglement builds space, area counts secrets, codes decide access. The inside is a story you're allowed to read only if the edge you hold is big enough, and if you're willing to pay the heat to decode it. Quantum noise as camouflage. Uncertainty, no cloning, no delete. She thought of noise as the enemy, something to suppress with colder baths and better shielding. Then it dawned on her. In quantum mechanics, noise is camouflage. It's not an accident layered on top of truth. It's the fabric that keeps truth from being duplicated, rewound, or known from all angles at once. The blur isn't sloppiness, it's policy. Here's the thing. The uncertainty principle is usually taught like a punishment. Try to measure position precisely and momentum spreads, or vice versa. But that trade isn't a technical failure. It's a guardrail that prevents you from extracting a full classical record that would let you clone a state later. If you could pin down both with arbitrary precision, you could make perfect templates. Templates mean copying. Copying breaks the code. Meanwhile, something else is hiding in the math. The no-cloning theorem isn't a slogan. It's a theorem that says there's no universal machine that takes an unknown quantum state and outputs two perfect copies. The reason is simple and brutal. Linear evolution preserves inner products. If you copy one state and copy another, their overlap must square, which can't be achieved by a single unitary for all inputs. That algebraic stiffness is the universe refusing to let information proliferate without trail. Get this, there's a twin rule on the other end: no deleting. If two identical copies of an unknown state exist in a closed system, there's no operation that deletes one while leaving the other intact, and no garbage record that reveals which was erased. Together, no cloning and no deleting mean quantum information can move and scramble, but it can't be conjured from nothing or annihilated to nothing. Conservation, not of energy, but of distinguishability. Now remember decoherence from the lab. When a state leaks a little witch path information to the environment, the system's reduced state looks noisy. That noise is exactly the camouflage that enforces no cloning in practice. Any attempt to peek, even gently, entangles the system with a pointer and smears phase relations you'd need to duplicate. The environment becomes an archive you can't access fully, so the local record looks washed. The blur is the shield. She sees the same logic in cryptography. Quantum key distribution works because any eavesdropper must interact with the qubits to learn their states, and that interaction leaves telltale noise, error rates that spike above an agreed threshold. The channel's hiss isn't just a nuisance, it's proof of tampering. The code leverages the policy. You can't copy without leaving fingerprints. Meanwhile, LIGO's engineers did something sly with this camouflage. They used squeezed light to reshape quantum noise, reducing fluctuations in one quadrature while boosting them in the conjugate. It's a tactical compromise with uncertainty. Accept bigger blur where it hurts less to gain clarity where it matters. Even then, the wall remains. You can't squeeze both sides at once. The guardrails hold. Get this, if you try to game the system by making many weak, nearly non-disturbing measurements to build a composite picture, the cost reappears as cumulative backaction. Each tiny probe steals a sliver of coherence. Add enough slivers and the wave-like behavior you needed to predict the rest dissolves. The code enforces diminishing returns. Try to assemble forbidden knowledge out of allowed pieces, and the camouflage thickens. 3 days earlier, she learned a painful lab lesson. A colleague attempted to learn an unknown qubit by seeding an ancilla with a gentle entangling gate, copying a little amplitude each time to build a library of approximate clones. The first few ancillas looked promising. By the 10th, interference vanished. The source state had become classical noise. He hadn't cloned. He'd bled the state into an environment of his own making. No cloning and decoherence teamed up to end the heist. Here, where the information theoretic picture clicks. Uncertainty bounds the mutual information you can extract about complementary observables. No cloning bounds the channel capacity for duplicating unknown states to zero. No deleting forbids unilateral garbage collection. These aren't separate curiosities. They're one policy written in different fonts. Quantum information is monogamous with its correlations. If it's entangled here, it can't be perfectly entangled there too. She connects this to the holographic code she's been studying. Bulk logical bits are redundantly encoded, but the redundancy isn't classical duplication. It's error-correcting spread. Different boundary regions hold different recovery maps, each incompatible in detail. That's why there's no cloning paradox. You can reconstruct from one coalition or another, but not from both in a way that yields two independent, perfect copies. The camouflage, random-looking boundary noise, protects the interior from local theft. Meanwhile, in her own data pipeline, she notices a parallel. Raw quantum trajectories look like jitter. Only after careful correlation with control records do patterns appear. Strip away the controls and all you see is noise. That's the point. The record alone shouldn't let you reconstruct the state. You need the joint story, the right questions, the right wedge of access. The rest is by design unreadable. Now remember the human moment. She used to curse noise as failure. Now she hears it as a policy tone. The hiss says, you've reached the boundary of what can be shared simultaneously. You can ask for a path or for a phase, for a copy or for privacy, for erasure or for reversibility. You can't ask for all of it at once. The camouflage isn't hiding a pristine classical truth. It is the truth that keeps the code from tearing. The quantum eraser, undoing questions to restore the mask. She returns to the lab with a stubborn plan. Don't fight the policy, work it. If which path information kills interference, then stop asking the question. Not by pretending, but by physically undoing the trail. The quantum eraser isn't a metaphor. It's a circuit that takes a path-tagged photon and scrambles the tag so the path can't be recovered. When the record can't exist, the mask returns. Here's the setup she builds. 2 slits, each adding a distinct polarization twist, horizontal for the left, vertical for the right. That tag is a path marker. With both slits open, the screen shows 2 fat blobs, not stripes, because the photon carries a witch label. Now she inserts a polarizer at 45 degrees before the detector. That device erases the difference between horizontal and vertical, mixing them into the same basis. Crucially, she doesn't just blur. She makes the tag unrecoverable in principle. In the right subset of outcomes, selected by a coincident partner detector, the interference pattern reappears. Get this, the eraser doesn't reach back in time. The single photon screen still looks like a dot field with no obvious stripes. Only when she correlates with the partner's clicks, sorting detections into 2 piles, do 2 complementary interference patterns emerge, offset like twins. Add the piles together and the fringes cancel, returning the bland blur. Subselect with the right key and the stripes are crisp again. The mask isn't a lie, it's a conditional truth unlocked by correlation. Meanwhile, something else is happening under the hood. The eraser isn't tearing out a page, it's changing the question. Before the polarizer, path and phase are incompatible. After, she's asked the joint system a different complementary question, one that never encodes a definite path. When you don't demand which path, the system pays you back with phase. The math calls it projecting onto a basis that preserves coherence. In her head, it's a librarian shelving your query in another aisle. Now remember the rule from earlier, partial knowledge, partial interference. She tests it by rotating the polarizer away from 45 degrees, set at 45 degrees relative to both H and V so it projects them equally. The more the device preserves path information, the more the fringes fade and the condition counts. At exactly 45 degrees, path is maximally erased and fringes are sharp. At 0 degrees or 90 degrees, path is preserved and the stripes die completely. A smooth slider between know and show. No drama, just policy. She tries the delayed choice variant because the rumor won't let go. Send the photon through the slits, tag its path, and only after it passes the tagging stage decide whether to insert the eraser. The timing feels like a dare. Can a late decision rewrite the past? She watches the logged coincidences settle into the same story. When the apparatus is configured so that which path could be known, no interference in the conditioned data. When it's configured so that which path can't be known, interference. The order of operations on the lab clock doesn't change the logic. Availability of information in the full circuit is what counts. Get this, what the eraser restores is the interference that was there all along. It restores your ability to sort events into a pattern that reveals phase. Without the key, the dots look random. With the key, they arrange themselves into stripes. Information wasn't traveling back. It was waiting in correlations, like ink that only appears under the right light. The mask is the conditional view you can recover when you've refused to leave a trail. Meanwhile, a colleague tries a twist with entangled pairs. One photon goes through the slits and lands on a screen. Its twin heads to a distant station with a set of polarizers. Depending on which basis the twin is measured in, the lab can later sift the screen's hits into sets that show interference or don't. Nothing superluminal happens. The screen alone never reveals fringes. But the joint record, reconciled after both sides finish, shows the same policy. Erase the possibility of path knowledge, and the mask returns in the correlations. She sits with the human sting of it. The eraser isn't mercy for curiosity, it's a mirror. Ask the path question and you buy the answer with your phase budget. Change your mind and remove your own ability to ever know the path, and the universe gives you back the wave. You can't keep both. The payoff is fair, and it's final. Now remember Landwehr's bill hiding in the corner. To condition on the right coincidences, she collects and sorts vast logs, then discards the rest. Sorting is correlation work, discarding is erasure. The moment she compresses all the runs into the runs that match this outcome, heat spills into the room. The code stays consistent. Restoring the mask in analysis demands paying the toll. She leaves the lab at dawn and feels the rule bloom into a worldview. The eraser isn't a magic trick, it's an ethics of questions. If you truly commit to never knowing a path, build apparatus that makes the record unrecoverable even in principle, you earn coherence back. If you hedge, the mask blurs. The universe doesn't punish curiosity, it prices it. And when you try to undo a question, it checks the ledger first. If no path record can exist, you get your stripes. If one can, even faintly, the mask stays off. Cosmic censorship, naked singularities, and the things we never see. She was raised on a simple promise. Gravity hides its worst. Singularities, the places where curvature spikes and the math says, I can't continue, are buried behind horizons. That's Penrose's cosmic censorship conjecture in plain speech. No naked singularities showing themselves to the universe. No raw breakdowns of predictability exposed to distant observers. If there's a rift in the fabric, a horizon pulls a curtain. Here's the thing, this isn't prudishness from nature, it's policy about cause and effect. A naked singularity would mean future light cones that sprout from an undefined point. Predictability would fail outside, not just inside. You couldn't set initial data and trust evolution. The auditor we've been hearing, the one who balances ledgers and enforces access, would lose its authority. Cosmic censorship says that can't happen. If the equations drive toward catastrophe, spacetime grows a vault. Meanwhile, something else is happening in the stories of collapse. Spin a star too fast, charge it too highly, strip its mass just right. Classical solutions hint that you might dodge a horizon and bear the core. But every time theorists push, another clause appears. Small perturbations flip the attempt back into a hole. Quantum effects sneak in to smear the would-be exposure. Even cosmic neighborhoods conspire. Dust, radiation, tiny asymmetries. The curtain keeps finding a way to fall. Get this, censorship and the area ledger rhyme. The maximum information you can pack scales with area, violate the budget, and you form a horizon. Try instead to tear the budget page out, to show the singularity without paying area, and the code resists. The surface is the price of hiding what can't be shared. If the singularity is the place where the rulebooks collide, the horizon is the fee you pay to keep their disagreement private. She stares at the causal diagrams until they feel like courtroom sketches. Outside the horizon, signals behave. Null rays angle just so. Inside, all future paths tilt inward. A singularity sits at the end like a sealed record. You can fall in and read nothing. You can't stand outside and subpoena it. That's the point. The universe protects the solvable part of itself by limiting who gets to ask the unsolvable part a question. Now remember black hole evaporation. Hawking's glow threatens to thin the curtain with time, to drain the horizon until nothing's left. Does the singularity then go naked at the finale? The page curve logic and island tools answer quietly. The bookkeeping never hands you a raw feed. As the area shrinks, correlations flow out in a way that balances the books, and the encoding of the interior migrates to the exterior long before any hypothetical exposure. You never see the singularity. You inherit its story through a code. Meanwhile, the engineering voice in her head asks how censorship shows up in measurement. It looks like a ceiling on what external probes can jointly know about the deepest interior. No matter how you shape your light, how long you wait, how cleverly you correlate, the reconstruction wedge stops at the curtain until the permitted time and access arrive. It isn't a lack of power, it's a partition in the code. She thinks about cosmic disasters, colliding neutron stars, collapsing cores, jets that briefly outshine galaxies. We watch all of it from outside the protective glass. The most extreme engines are horizon machines. When they light up, the singular calculus runs in the back room and we get the emissions they're allowed to leak. Neutrinos, gamma rays, gravitational waves drummed on the fabric. None of it a direct peek at the forbidden point. The universe broadcasts the edges. It redacts the center. Get this, gravitational wave backgrounds stitched by pulsars across the sky are censorship in chorus. We don't resolve single supermassive mergers. We recover their statistical hum, a quadrupolar signature that says, yes, heavy things dance. Not names, not faces, just the shape of the party. The Hellings-Downs curve is itself a kind of curtain, a correlation you can know precisely, concealing the exact sources behind it until other access appears. 3 days earlier, she'd argued with a friend who loved loopholes. Could an advanced civilization engineer a naked singularity to mine infinite computation from causality's edge? She drew a horizon on a napkin and wrote "access denied" along it. The limits all chimed in: energy conditions, instabilities, quantum noise, capacity. Even if the math leaves a crack, the physical world stuffs it with cost. The code abhors a spectacle. Now remember the human moment. She once wanted the universe to show its teeth, to confirm that the core is as wild as the equation's threat. Now she's relieved by the restraint. Censorship isn't prudery, it's mercy for prediction. It keeps clocks meaningful and channels reliable. It lets experiments close their loops without ghosts from undefined futures creeping in. She writes the plainest version on the board. When truth would break the rules that make truth shareable, the universe withholds it. Horizons form, correlations replace exposures. Surfaces talk, centers stay silent. That silence isn't empty. It's the sound of a contract being honored, the same one that priced which path, rationed capacity, billed erasures, and bound information to area. And if someday a naked singularity slips through the clauses, then our contract changes. Until then, the curtain holds. The processing budget, computation limits of matter. She used to think computation lived in laptops and server racks. Then someone handed her a bound that belonged on a wall of laws, not a data sheet. There's a maximum speed for turning possibility into certainty. The Margolis Levitin limit says a system with average energy E needs at least h/4 E seconds to evolve into a fully distinguishable state, not a design flaw, physics. To flip a clean logical bit, To rotate a qubit to orthogonality, you must spend time that no cleverness can erase. Here's the thing, computation is just controlled physical evolution. Gates are Hamiltonians in drag, so every CPU, ion trap, or quantum array inherits that time tax per orthogonal step. Double your energy and you only have your minimum step time. You can't buy infinity with watts, you just nudge the meter. Meanwhile, Landwehr's bill lurks on the other side. Erase a bit and you owe KT ln2 in heat. Compute fast and you heat your bath. Erase often and you fog your own sensors. The two constraints cross like beams, making a box you can't lean out of for long. She sketches a budget on a napkin. Energy sets the tick rate. Temperature sets the cost of cleanup. Error rates set how much overhead you need for correction. Real processors, classical or quantum, spend most of their life not doing logic, but shepherding states against noise, encoding, decoding, refreshing. That overhead explodes as you push fidelity. Capacity again. A device is a channel from input states to output states through a storm of perturbations, and Shannon's limit tells you how much reliable structure can survive given the noise suit. Meanwhile, in the lab down the hall, a quantum team celebrates 100 error-corrected gates. They aren't naive. They know each logical gate hides a swarm of physical pulses, syndrome measurements, and resets that spew heat. That heat lifts the background, which feeds back as dephasing, which demands more correction. The circle tightens. You can stretch it with colder fridges, better materials, smarter codes. You can't break it. The processing budget is a thermostat attached to a metronome. Get this, bound the number of operations a chunk of matter can perform before it melts its own context, and you've backed into a cosmic rule. Bekenstein taught her that there's a maximum entropy, maximum information content, inside a region for a given energy and size. Combine that with speed limits and you get a brutal upper bound, a finite number of reliable, distinguishable steps before gravity or heat rewrites the problem. You can try to compute near black hole densities, but then your computer is a horizon machine with glacial I/O storage without readout isn't processing. It's burial. She runs the same logic on brains because the question won't leave her alone. Neurons fire slowly. The architecture is noisy, yet the organism computes robustly because it surrenders precision for energy efficiency and leans on redundancy. Biology, like engineering, obeys the code. Don't chase orthogonality harder than you can cool. Don't erase more than you can exhaust. Intelligence lives in the valley between speed and heat, not at a corner of the plot. Now remember pulsar timing arrays listening for the gravitational hump. Their processor is a galaxy-scale correlator that integrates for years to beat noise down to meaning. That's computation in a different accent. Time as error correction, patience as cooling, correlation as code. They can't shorten years with power. The background sets a floor, and only more data, more stable clocks, and better models raise their effective rate. The budget holds at cosmic scale too. Meanwhile, she reads a quiet theorem that feels like a sigh. Even reversible computation must pay when it hands an answer to someone else. You can carry ancillas forward, uncompute garbage, keep history pristine. The instant you compress the story into a short message for another agent, you prune branches, you erase. Communication is selective forgetting. The bill arrives because the point of computing is to decide. Get this, rumors about infinite computation in strong fields or near singularities collapse under the same ledger. Infinite blue shifts buy you cycles at the cost of causality and access. If your clock runs wild where no external observer can coordinate, your answer is a private hallucination. The censorship code would call that off-ledger work. Not shareable, not verifiable, not knowledge in the communal sense. The budget isn't just numbers. It's the requirement that results be exportable through noisy channels that themselves have capacity. She tests the boundary in her own experiment. Push the detector rate higher to catch more events per second. The data flood hits the wiring, then the buffer, then the software that tags and erases. Temperatures creep up. Error bars widen. She dials back, widens the integration windows, invests in better codes instead of brute force. The improvement feels slower, more honest. The machine lands in a regime where the ledger balances. Energy in, ticks out, heat dumped, capacity respected. Now remember the human moment. She once believed the universe would yield to will and budget. Now she sees a deeper generosity. It lets you compute just fast enough to share truths without tearing the fabric that makes truth communicable. The processing budget isn't pettiness. It's a ceiling that preserves meaning. She writes one line in the margin of her notebook. To know is to compute within your means, energy, time, entropy, access. Beyond that, the code turns answers into heat. The vacuum that isn't, Casimir, 0 point, and the bit-flavored void. She grew up with an empty box as a picture of nothing. Then the vacuum pushed back. Here's the thing: two uncharged metal plates placed micrometers apart in a vacuum feel a gentle pull toward each other. No wires, no batteries, just space between them. That's the Casimir effect. The story physicists tell is about modes. Electromagnetic waves in the vacuum can take on discrete standing patterns between the plates, but only those that fit. Outside, every wavelength runs free. Inside, many modes are forbidden. Fewer allowed fluctuations inside means lower vacuum energy there, higher outside, and a pressure difference nudges the plates together. The vacuum acts like it has opinions about boundary conditions. Meanwhile, something else is happening in her head. Those forbidden modes sound like missing messages. The space between plates is a channel with reduced bandwidth. The space outside is a channel with more. The vacuum isn't a background. It's a ledger of possible excitations, and boundaries edit the ledger. Push on geometry and 0 point fluctuations push back. Now remember the noise she's been fighting in measurements. Quantum fields jitter even at 0 temperature, 0 point motion that never shuts off. In a cavity, that motion is sculpted by the walls. The upshot is concrete. Tiny forces measured with torsion balances, shifts in atomic energy levels, cantilevers that feel a whisper from empty space. Engineers design around Casimir forces when building MEMS devices because, at small scales, the vacuum will pull parts together and weld your plans shut. Nothing isn't inert. Get this: if the vacuum's bookkeeping depends on boundaries, then information is baked in. A cavity selects which modes exist. That selection is a restriction on distinguishable states. Fewer states, less entropy. The force is the vacuum paying you back for reducing its options. Change the boundary, change the count, change the pressure. It's thermodynamics with a spectral accent. She sees echoes in blackbody radiation. A hot cavity glows with photons that occupy allowed modes according to temperature. Cool it to near 0 and the thermal population ebbs, but the ground-level jitter remains. 0 point energy isn't a stash you can empty. It's the statement that no excitation is still a state with structure. Try to harness it as free power and the second law taps your wrist. The useful gradients live in differences. Between inside and outside, hot and cold, allowed and forbidden, not in some infinite reservoir of vacuum to be mined. Meanwhile, LIGO's team learned to squeeze the vacuum. Inject squeezed states into the interferometer's dark port and you reshape vacuum fluctuations at the output. Reduce uncertainty in the readout quadrature, accept more in the conjugate. The sensitivity improves where you care. The cost rises where you don't. It's the vacuum behaving like a coded noise source. You can reformat it, not delete it. The standard quantum limit shifts because you negotiated with the void statistics, not because the void blinked. Get this: the vacuum remembers entanglement. Separate two regions in their ground state contains correlations across the boundary. That's why tracing out a region gives you entanglement entropy proportional to area, the same area law that keeps haunting her. Even in empty space, the number of ways the outside can be correlated with the inside scales with the boundary, not the volume. Carve space with surfaces, and the vacuum writes a count along those cuts. Holography started to sound less exotic and more like an honest reading of the ground state. She tests the idea with cavities in the lab. Change plate spacing and the force shifts. Change materials and response changes. Cool the system and thermal noise recedes, leaving the geometry-scripted push. Each knob turns a bit count dial. The device becomes a translator from which modes are allowed to what force do you feel. She's not measuring nothing. She's measuring the difference between two kinds of nothing defined by boundary conditions. Now remember the human moment. A technician complains that a delicate microresonator kept sticking to its electrode during assembly. They blamed dust at first. Later, they learned the gap was small enough for Casimir to matter. The vacuum closed the last micron. They redesigned the geometry, added ridges to reduce parallel plates, and the sticking stopped. Policy in hardware. Meanwhile, cosmology whispers a different tension. If you sum zero-point energies of all modes, naive math explodes, predicting a vacuum energy density that would rip the universe apart, many orders of magnitude larger than what we infer from cosmic acceleration. Renormalization tames the calculation in effective theories, subtracting infinities and fixing measured constants, but the smallness of the observed cosmological constant remains a puzzle. The vacuum is real enough to squeeze plates and shape sensitivities, yet subtle enough to almost cancel itself on cosmic scales. It's as if the ledger balances to absurd precision, with a leftover line item that steers galaxies. She keeps coming back to the channel metaphor. The vacuum is an empty real estate. It's a catalog of allowed fluctuations, sculpted by boundaries and stitched by entanglement. Surfaces decide which messages could, in principle, be sent through nothing. Shift the surfaces and you shift the catalog. That's why forces appear. That's why area keeps showing up as an entropy bookend. The void is flavored by bits. Get this, when she cools her detector, zeroes out biases, and dims stray light, the remaining hiss isn't nothing. It's the ground state talking, filtered through the apparatus. That hiss is policy embodied. You can never turn the channel off. You can only choose which parts of its noise to live with. Reformat the vacuum with squeezing, shape it with cavities, fence it with plates. You're not silencing it, you're negotiating. She flips off the lab lights and the room glows with LEDs on idle boxes. The air looks still, the vacuum hums on. Empty space as a final hiding place is a myth. The universe's quietest state is already a code. Modes allowed and forbidden, correlations braided across cuts, forces born from counting. Even at zero, the bill and the bounds apply. The void is the baseline contract. When we scale up the question, LIGO, timing arrays, and cosmic bandwidth. She used to think the lab bench was where questions lived. Then she stood on the catwalk above a LIGO arm and felt small. 4 kilometers of vacuum tube, mirrors hung like jewels on glass fibers, lasers stabilized until their heartbeat was quieter than a thought. All to hear spacetime move less than a proton's width. If the universe runs a censorship code, this is where you test its edge cases, with scale as your lever. Here's the thing, LIGO is a negotiation with noise across a colossal baseline. Seismic rumbles underfoot, thermal jiggle in the mirrors, quantum shot noise in the light, radiation pressure that nudges the optics. They didn't beat these one by one, they balanced them. Heavier mirrors to quiet thermal motion, but not so heavy that radiation pressure becomes a bully. Squeezed light to reduce shot noise in the readout quadrature, accepting more in the conjugate. Long arms to turn tiny strains into measurable phase shifts, but with exquisite alignment so the gain isn't lost to wandering beams. Every decision is a capacity trade. Push here, pay there. Meanwhile, something else is happening behind the scenes. LIGO's detection isn't a raw wiggle that pops from the vacuum. It's matched filtering, comparing noisy data to a bank of waveform templates generated from general relativity. The signal becomes visible because you already know what you're willing to hear. That's bandwidth turned into knowledge by code. You widen effective sensitivity by integrating in time and in model space. Past a point, you're limited by the quantum flooring and the environmental hiss you can't scrub. The ceiling isn't taste. It's the same mathematics that priced her lab runs. Get this, when LIGO first heard two black holes merge, it wasn't just a triumph of hardware. It was a lesson in scale. Increasing the size of your instrument increases the spacetime volume you interrogate, but the information rate you can trust still flows through narrow channels. More kilometers gave more phase. More integration gave more certainty. More templates gave better extraction. None of it broke causality, capacity, or Landor's bill. It stretched them to a clean edge. Now remember the radio guide who said, "We integrate for hours." Scale that to a galaxy. Pulsar timing arrays turn millisecond pulsars into a lattice of clocks sprinkled across the sky. Each pulsar is a lighthouse ticking with stunning stability. The times of arrival wander because the universe shakes the path. Plasma in the interstellar medium adds dispersion. The Earth's own clocks drift. But correlate dozens of pulsars over years, and a quadrupolar correlation pattern emerges. The Hellings-Downs curve. It's a signature you can't counterfeit with local noise. A collective ear hears a background hum from supermassive black hole binaries far beyond any individual telescope's reach. Meanwhile, patience becomes bandwidth. Weekly observations over a decade convert low nanohertz frequencies into a resolvable band. You can't make a wave with a period of years show up in a day's data. You must commit to the timescale the signal demands. Capacity again. The reliable rate at which you can extract meaning is bounded by cadence, clock stability, and the total observation span. No rumor outruns light. No analysis outruns its own integration window. Get this, both experiments are giant error-correcting codes in steel and sky. LIGO redundantly measures orthogonal quadratures, cross-checks twin detectors thousands of kilometers apart, and vetoes environmental glitches with a spiderweb of sensors. Timing arrays triangulate with angles on the sphere, using geometry to cancel local quirks. Neither trusts a single channel. Both assemble a coalition big enough to earn access to a deeper wedge of reality. And both pay. LIGO pays in cryogenic baths, squeezed states, seismic isolation, and the heat of endless data erasures. PTAs pay in calendar years, telescope time, calibration campaigns, and the entropy of discarding bad epochs. She sees the human scale of these costs. Students age into postdocs watching timing residuals settle. Optics crews spend nights chasing subnanometer drifts. The bill for certainty is time and energy amortized over careers. The code doesn't relent because you wrote a grant. It yields because you shaped your question to fit the channel. Meanwhile, the revelations are precise but modest. LIGO names events. GW150914, GW170817 pins down masses, spins, distances. PTAs whisper a statistical truth. A background is there, its spectrum leaning with frequency, consistent with galaxy mergers, though cosmic strings tease in the margins. Not names and faces, shapes and rates. The universe answers what it can without breaking privacy for individual sources. You haven't earned the access to isolate. Now remember her earlier shift from pixels to policy. Scaling up didn't find smaller pixels, it clarified permissions. Long arms stretched phase sensitivity. Long timelines unlocked nanohertz. The guardrails held. Causality fenced what can influence what. Shannon fenced what can be recovered through noise. Landor fenced what it costs to keep only the bits you need. Holography, by way of area laws, whispered that even when you listen with a galaxy, you learn a surface's worth per region and time. Here's the quiet punchline. Scaling isn't a way around the code, it's a way to align with it. Build instruments whose geometry matches the signal's geometry. Let integration match the signal's timescale. Encode your prior knowledge carefully so filtering spends bits where it matters. Then pay the toll in heat and patience without flinching. She steps off the catwalk and looks down the vacuum pipe. A straight line into haze. It feels like a metaphor she can finally trust. The path to more knowledge isn't a brute sprint. It's a longer baseline, a steadier clock, a better code, and the calm acceptance that the universe sets the pace. Spacetime as a code, error correction, redundancy, and forbidden queries. She circles back to the boundary picture and starts speaking in the language of codes. If a bulk bit can be recovered from different boundary regions, that's not duplication, that's error correction. The interior is a logical message spread across many noisy carriers on the edge. Lose a few, scramble a patch, even heat one sector up, and the code still lets you decode, if your coalition is big enough and your recovery map fits the stitching. Here's the thing, good error-correcting codes do two jobs at once. They protect against small local noise, and they restrict which global observables can be known together. Ask for one set of checks, and the code hides another. That's what holography feels like in practice. Overlapping reconstructions that are compatible globally but mutually exclusive as local, simultaneous knowledge. You can pull a bulk operator from region A or from region B, but you can't use those two reconstructions to mint two independent copies. The redundancy is surgical, not promiscuous. Meanwhile, she studies toy networks where the geometry is literally the wiring of a code. Short bonds act like fragile links. Thick bonds act like higher capacity channels. Cut a minimal set of bonds around a region and you've measured its entanglement with the rest. That cut is the area term. The leftover fine print is quantum correction. Flip a few legs, local errors, and logical information survives. Cut too many, exceed the area budget, and reconstruction fails. The surface budget is built into the decoder. Get this, codes don't just say what you can fix. They also say what you're not allowed to ask. Try to query two non-commuting bulk facts by reconstructing from overlapping boundary regions in incompatible ways, and the algebra refuses a joint answer. Not because the truth isn't there, but because the only consistent global state that fits both queries is one you can't access with finite local control. In a lab, that shows up as vanishing fidelity when you chain decoders that weren't designed to cohabit. In the cosmos, it reads like cosmic censorship in code form. Certain joint questions are forbidden because answering them would tear the encoding. She frames a lab analog to make it sting. Take a fault-tolerant quantum memory. Logical Z and logical X live on long, non-local operators that snake across the device. Local noise flips a few physical qubits. The decoder smooths them out. But if you try to read both logicals sharply at once with finite resources, you pay. Your measurements stretch into the same neighborhoods and disrupt each other. The memory won't hand you perfect, simultaneous, incompatible facts, because that would break its own protection. The code survives by denying certain compound demands. Now remember the thermodynamic toll booths. Decoding isn't just algebra, it's work. You gather syndromes, process correlations, and erase mountains of intermediate guesses. The better the code and the messier the noise, the more syndromes you need, the more heat you dump. In boundary language, larger regions give you bigger wedges but require more coordination and more erasure. Access isn't free. Permission must be exercised with resources that leave thermal fingerprints. Meanwhile, there's a softer rule hiding in the redundancy. If many boundary coalitions can reconstruct the same bulk message, then no single small coalition can secretly alter it. That's tamper resistance by design. The logical bit is stabilized by being everywhere at once and nowhere locally. It's why an infalling observer can experience a smooth horizon without letting an outside lab violate unitarity. Each perspective has a valid, redundancy-protected reconstruction. Neither has the levers to force a global contradiction. Consistency comes from distributed custody. Get this, the same structure limits speed. To recover a deep bulk fact, you don't just need a big boundary patch. You need time to pull syndromes across it, correct them, and run the recovery map. In practice, that means light crossing times, control latencies, and cooling cycles. The effective distance to an interior operator is a decoding depth measured in operations and temperature. If you rush, errors pile up and the recovered message devolves into noise. The code enforces patience. She tests the idea on a paradox that used to keep her up. Suppose two disjoint boundary groups each claim to reconstruct a bulk operator behind a horizon. Aren't they holding the same qubit twice? Not in a way that breaks quantum rules. Their reconstructions are different algorithms acting on different Hilbert spaces with overlap. Apply both without coordination and they fail each other. Coordinate at scale, and you've effectively formed one larger boundary that owns a single access right. The code lets you choose a decoder. It doesn't let you multiply truth. Now remember the experiments that listen for whispers. Interferometers, timing arrays, telescopes stacking weak signals into clarity. Each is a decoder layered on a noisy boundary. Each uses redundancy, multiple detectors, long baselines, independent pipelines, to make a fragile message robust. And each is bounded by forbidden queries. You can't demand phase and path at once. You can't demand infinite resolution without forming a horizon. You can't demand a name from a background before you've earned a higher signal-to-noise wedge. She closes the notebook on a plain sentence. If spacetime is a code, then meaning lives in what can be recovered with finite control, finite time, and finite heat, from regions that are big enough but never all of them at once. The rest isn't hidden behind malice. It's hidden by design. The island rule in late time leaks, a modern ledger. She'd seen the page curve on chalkboards. The island rule gave her the mechanism. In the cleanest models, you don't assign entropy by staring at a horizon. You draw a surface, the quantum extremal surface, and let geometry plus quantum fields decide which interior chunks count as part of the radiation's ledger. Early on, the minimal surface hugs the horizon. The radiation is outside, ignorant. Past the page time, the surface jumps. Suddenly, an island inside the black hole belongs to the radiation's entanglement wedge. The vault hasn't opened. The title deed changed. Here's the thing, this isn't hand-waving. The recipe tallies generalized entropy, area 4 for the surface, plus the entropy of fields on each side. You vary the surface until the sum is stationary and minimal. Before the page time, including interior regions costs too much area. After, the area term has shrunk, while the field entropy outside balloons, a configuration that ropes in an interior island wins. The math says the outside description now encodes part of the inside. That's the ledger update the curve demanded. Meanwhile, she hears the practical whisper. Encoding isn't extraction. The correlations that purify late Hawking quanta live in the radiation you've already collected, but turning them into a message means decoding a code you didn't design. The Hayden-Preskill mirror returns as logistics. You wait a scrambling time for new infall to mix. Then, if you own enough old radiation and can compute hard enough, you can, in principle, reconstruct. The permission has flipped. The price remains. Get this. The island rule resolves a paradox by changing the question, not the physics at the horizon. Infallers still meet smooth space. Local effective field theory still works for them. The contradiction dissolves because who owns the interior depends on which subsystem you're asking about. The radiation's algebra and the black hole's algebra share a logical bit late in the story. No copying, just distributed custody enforced by a code. She grounds it with a benchtop analog. Take a small quantum memory encoded with an error-correcting code. Early on, the logical qubit is recoverable only from the device itself. The environment holds nothing but thermal junk. She then couples the memory weakly to a large radiation register and waits while a scrambling circuit mixes them. Run entropy diagnostics along the way and you see a jump. Past a threshold, the minimal cut that best explains the correlations now slices through the memory and includes part of its interior degrees in the radiation's recovery set. The lab doesn't build a black hole, but the bookkeeping matches. A surface, the cut shifts, and the island, logical information once local, now belongs by encoding to what leaked out. Only then can an outside decoder, holding enough of the radiation and a lot of patience, reconstruct what used to be inside. She tests the edge cases that made headlines. What about measuring a late Hawking mode and its interior partner? Early, they're entangled across the horizon. Late, the partner is part of the radiation's wedge. Try to grab both and you run into monogamy. The same mode can't be maximally entangled twice. The island prescription assigns partners to the radiation, preventing a double claim. The firewall's spark fizzles because the bookkeeping forbids the impossible pairing before it becomes a contradiction. Now remember Landwehr's bill and the processing budget. The island story isn't free candy. It's a statement about where information lives. To make it knowledge, you must gather, correlate, and erase. The later you try, the more radiation you must wrangle. The colder you must keep your machines. The more heat you must dump to compress outcomes. The cosmos preserves unitarity while throttling access by cost. She steps back and says it plain. Early, the horizon is a curtain. Late, the curtain's contents are re-indexed to the audience that waited. The universe didn't change its mind. It rotated the ledger to keep truth shareable and the books balanced. Everyday redactions, why your world won't give up the goods. She starts close to home where the code hides in plain sight. Open your phone camera in low light and watch the image grain crawl. That is bad sensor tech. It's shot noise, the quantum arrival statistics of photons leaking through the lens. You can widen the aperture, push the ISO, stack exposures, denoise with clever prayers. The hiss never vanishes. You're trying to write certainty with too few quanta on too short a clock. The policy shows up as blur and speckle. Here's the thing, your ears live under the same rule. Turn down a recording and then turn it back up. The floor that remains isn't silence. It's the system's own thermal and electronic noise, shaped by bandwidth and temperature. Tighter filters cut noise but shave off detail. Wider bandwidth brings nuance and hiss together. You're choosing an entanglement wedge for sound, a region of frequencies you can recover with a given bit rate, a given heat budget. Meanwhile, something else is happening on the street outside. GPS feels magical until you look at the margins. The signal from satellites is faint by the time it hits your phone, buried in atmospheric multipath and urban reflections. The receiver integrates over time, correlates with known codes, and rejects outliers to climb above the noise. You don't get your location in an instant, you accumulate it. Try to force a faster fix and the variance explodes. Patience buys precision, because capacity has to be earned with time. Get this, your browser tab, your cloud backup, your streaming show all pass through channels with finite capacity and error rates that never go to zero. That's why protocols add redundancy. Packets carry checksums. Storage adds parity. Video codecs predict and correct. Every correction demands computation. Every computation dumps heat. Your laptop's fan is Landwehr in miniature, clearing the bits you don't keep so you can keep watching the frames that matter. The lag you feel when a connection stutters isn't just the internet being slow. It's the code refusing to deliver more reliable bits per second than the channel can support. She moves to biology because the mirror is too neat to skip. Eyes don't measure, they infer. Photoreceptors fuse signals over tens of milliseconds to catch enough photons. The brain composes a stable world from jittery inputs by betting on priors. Edges tend to be continuous, objects tend to persist. Those bets are a compression scheme tuned to the environment. You see what can be shared across time and space with the energy you can burn without cooking yourself. Push attention too hard and fatigue. Literal heat in networks pushes back. The organism computes within its processing budget and calls the result experience. Now remember the lab instinct to average. Your kitchen scale does it. Step on it and watch the digits settle. It weighs, filters, and rounds because the sensor is noisy and the output is finite. Resolution is a choice, not a default. More bits on the display would require a better sensor, stricter shielding, longer integration, more energy, more heat. The manufacturer chose a wedge of reality you pay for and stopped there. That's why the readout won't tell you what you want when you tap your toe. It refuses to claim more certainty than it can keep. Meanwhile, time itself enforces a softer censorship in your day. Attention switches carry costs. Multitask and your error rate climbs because your cognitive channel is finite and context switches erase volatile structure. That mental fog after too many tabs, too many notifications, is a human Landwehr effect. You've burned your budget-clearing subroutines to make room for new ones. You feel heat and call it stress. Underneath, it's the same old ledger, a race to proceed. Get this, social systems inherit the rule too. Crowdsourced truth only converges when enough independent, noisy channels correlate over long enough intervals. Rumors proliferate because copying is cheap and erasure, fact-checking, correction, is costly. Virality outruns verification because the code of our networks prizes speed over heat budget. Slow, careful institutions exist to landfill the error entropy so shared knowledge can be clean. The price is time, patience, and yes, real energy burned in offices that look boring on purpose. She walks past a row of MRI images and thinks about gradients. You don't see a body. You excite spins, read echoes, sample K-space, and reconstruct with assumptions. Resolution rises with stronger fields, better coils, longer scans, and the patient's tolerance for lying still while the machine heats its own guts and the room's air. Push farther and the costs explode. Hospitals make choices. Your scan is a negotiated truth within budgets of money, physics, and comfort. Meanwhile, your own emotions have a wedge. You can't know how every choice would have felt if you'd lived it. Memory compresses, it deletes. The stories you tell about yourself are decodings from noisy logs correlated with a few anchors and lots of priors. Ask for incompatible narratives at once. I was fearless, and I never risked hurt, and your code stutters. You pick, you erase, you heat. The human mask returns when you decide to not keep all paths open. Now remember the Casimir plates and the camera in the dark. Surfaces dictate. Sensors, windows, apertures, screens, all the edges you live with decide which modes pass through your life. Curtains edit sunlight. Walls filter sound. Browsers sandbox code. Even your skin is an error-correcting boundary that rejects noise, fixes cuts, and raises heat when it decodes invaders. The world you inhabit is curated by surfaces trained to keep you viable and to keep your channels sane. Get this, the redactions don't mean life is fake. They mean meaning is kept. The universe withholds what would melt the rest of your knowledge if it were handed to you raw. You get patterns and rates, not all microstates. You get signals shaped by scale, not universal clarity. Every "why can't I just see X" has an answer in the margins. Because capacity, because causality, because thermodynamics, because access. The ledger is identical whether you're weighing flour or timing pulsars. She ends the day with a small ritual. She shuts the laptop down properly, waits for the fans to spin down, and hears the soft click of a relay releasing. It's nothing, and it's everything. A machine wrote its last bits for the night, flushed buffers, erased scrap, and dumped the heat. The room is quieter. The code is still there in the hush, not as a conspiracy, but as a kindness that keeps the rest of the story readable tomorrow. Resolution and broader meaning. The universe isn't hiding out of spite. It's enforcing the rules that keep truth shareable without tearing the fabric that carries it. If you want the next layer, you pay in time, energy, and erased guesses. She locks the lab and steps into the blue wash of morning, frost smoking off the pavement. A thin contrail stitching the sky, signals crossing at their allowed rates, each having paid its toll to be seen. Subscribe if you want more stories that test those limits, and watch the next episode where we follow one bit from a quantum chip to a radio telescope and see how much heat it leaves behind.